Question 2. This is about distance time graphs and also the stopping distance and reaction time, I assume, of drivers when they see a hazard. So, to begin with, figure 3 shows a distance time graph for the journey made by a car. Distance on the y-axis and time going along on the x-axis. From this graph we can interpret things about its journey. Describe what figure 3 shows about the motion of the car between points A and E, so the entire length of the journey. Well, let's remember how to interpret distance time graphs. Distance on y, time on x. Think about it like this. As time goes along on this axis, what is happening to the distance on this axis? Is it increasing, decreasing, or staying the same? Oh, okay, interesting graph, but nonetheless we'll do it. So you should refer to data from figure 3 in your answer. So let's start with between A and B. So one thing I'd expect us to know on a distance time graph is the gradient tells us about the speed. Why? Because to work out the gradient, you're doing your change in y over change in x, your rise over run, and on a graph like this, that is distance y divided by time. Speed is equal to distance over time, so our gradient is the speed. So between A and B we have a straight line, a constant gradient, therefore it's travelling at a constant speed. So I can say this: between A and B the car travels at a constant speed. However, when the car gets to B, we should say probably here the car travels at speed for 30 seconds, as it's asking us to use some data. We could even work out the speed it's travelling at. When the car reaches B, it stops and remains stationary for 30 seconds. How do I know that? Well, at this point here, at B, and then up to C, as time goes on, the distance on the y-axis does not change. Therefore, this line here is telling me that the car is stationary. Okay, after leaving C, the car moves off to D at between C and D here. We have a straight line again, so at constant speed. Let's actually work that speed out this time. So between C and D, 60 seconds to 90 seconds. So in 30 seconds, it's traveling 300 or 280 to 540. So 280 to 540 meters is 260 meters. This car has travelled and it's taken 30 seconds to do so. Therefore, its speed is 260 meters per every 30 seconds. Which is 8.67 meters per second, because you're doing meters divided by seconds. So we could say here, to be really specific, after leaving C, the car moves off to D at constant speed, or at a constant speed of 8.67 meters per second. Perhaps looking at this, it looks like it's moving at the same speed as before in A and B as well. But without calculating it, I'm not going to make that claim. Okay. Finally, between D and E, the car, now this is where I'm going to be careful and refer to the mark scheme. Strictly this is a distance time graph and you'd always draw lines going up, but for some reason they've drawn one going down. Perhaps they wish that you to interpret this as a car reversing. Let's go for that and we'll double check in a second. So finally between D and E, the car reverses. And how far does it reverse? Reverses the 520 meters it has travelled. Again, it's a straight line, so the important thing to say there is at constant speed. As I said, I wasn't too happy with that graph, so let's compare this with the mark scheme. So for question 2, this is what we're wanting. Okay, so the car moves to constant speed, we've said that, and notice they've calculated the speed here as well. Away from its starting position, we could add. Between B and C, the car is stationary, so they've said the speed is 0 meters per second. Between C and D, again, we're moving at a constant speed. They've got the same speed we travelled at, 8.7 meters per second, or we worked it out to be. And then between D and E, the car moves to constant speed again, because it's a straight line. Therefore, the gradient's constant for 60 seconds at 9 meters per second. So, what did they want here? For level 1, you're making simple statements that describe the motion of the car, i.e. it's moving forwards, it's moving backwards maybe. Maybe not even that, you possibly wouldn't get a mark for that. I think it's simple statements like the car moves at constant speed. For level 2, there is a description of the motion in at least 2 sections of the graph. For 4 marks, there must be data from the graph included in the answer. So you need to include numbers for 4 marks and describe at least 2 sections of the graph. So be aware, if you're fairly comprehensive here, you're almost guaranteeing yourself the 4 marks there. Okay, so moving on though. 2.2. A car is travelling at a constant speed. When the driver applies the brakes, the car slows down and stops. Figure 4 shows the 2 different sections that make up the total stopping distance of the car. Firstly, we've got the distance the car travels during the driver's reaction time. That's what we call thinking distance. And then we have a second part. So, if you are driving or if you are being driven and someone sees a hazard, so if we had a car moving along, do a quick sketch, and someone were to see a hazard, and what I mean by that, perhaps that's an awful car. Perhaps a deer jumps out in the road. If I've drawn a bad car, I've drawn even worse deer. When the driver sees that deer, first of all, they have to react. That might take in between 0.2 and 0.9 seconds, depending on your reaction time. After they react, they hit the brakes. And that's this section here, which we call the braking distance. So the total distance it is for you to stop is made up of a thinking distance while you react and a braking distance while you come to a halt. So the braking distance is the distance the car travels after the brakes are applied until it comes to a halt or comes to rest, we can write. So until it stops. And that's 2.2 answered. 2.3. Give two factors that could affect the distance the car travels during the driver's reaction time. So during the driver's reaction time, if the driver's reaction time is slower for any reason or faster for any reason, that will change the distance the car travels. There are various reasons for this. So we could say, for example, drugs / alcohol. We could say tiredness. We could say distraction. Now, alcohol, tiredness and distraction will all increase your reaction time and you'll travel further. Thus, you're at more risk of crashing into the hazard. Drugs, depending on what they are, may cause you to react more quickly or more slowly. It is not always a benefit to react more quickly in terms of some drugs because there may be other effects acting as well. 2.4. When the driver applies the brakes, the car decelerates. Write down the equation that links acceleration, change in velocity, and time taken. Another one we have to learn. Acceleration equals change in velocity divided by time taken. For short, we write A equals V minus U over T, or A equals delta, change in velocity over time. Right, 2.5. Before the driver applies the brakes, the car is travelling at a speed of 17 meters per second. It takes 3.4 seconds, T equals 3.4 seconds, for the car to come to a complete stop. The car's final speed is therefore 0 meters per second. The car's change in velocity has therefore been from 17 meters per second to 0 meters per second. That's a total change of velocity of 17 meters per second. So we can write delta V equals 17 meters per second. Calculate the deceleration of the car between the driver first applying the brakes and the car coming to a complete stop. Well, all we have to do here is use the equation that we have just recalled for the previous question. Acceleration equals change in velocity over time taken. We've established our change in velocity as 17 meters per second, and that occurred over a time of 3.4 seconds. 17 divided by 3.4, is it 5 exactly? Yeah, it says 5 exactly. So 5, and the unit is meters per second squared for acceleration. 5 meters per second squared. Why meters per second squared? Well, meters per second squared is like meters per second per second. How many meters per second slower are you getting each second? So 2.6. Describe what happens to the brakes when they are used to stop the car. Well, brakes work by friction, therefore they become hotter. Their temperature increases, I should really write. Their temperature increases, and that is because of friction. That is question 2. I won't be going through question 3 on electromagnetism, as you are not being assessed on electromagnetism.